This computer. Now we have it. Now it's Monday, March 2nd, 2026. We are looking into chapter 19, but let's review quickly chapter. We didn't finish chapter 18, right? We have to talk about Gauss's law. So before we finish chapter 19. Okay, so let's review the. Let's get the material. Yeah, I want this list here. Here you go. This list here we have covered so far. Material covered so far. Covered so far. Okay. We're going to skip field inside the conductor, but we're going to cover this one here. For now, we're going to skip. Okay, field inside the conductor. But the bell, good. So let's highlight that here. Let's take a look. Equipotential surfaces. Okay, we cover equipotential surfaces during the lab. We did cover equipotential surfaces. We are going, no, just skip it, this one here. And let's just skip this one as well. This is a classical experiment. That's a historical experiment, the Millikan oil drop experiment. Maybe we'll have some time to do that. If we don't, we'll skip it. And I want to cover capacitors and dielectrics because it looks like we'll be able to finish those two chapters today, okay? So let's get here. Let's talk about Gauss's law. Let me. Gauss's law. Okay. So what you have to do, what you have to know about Gauss's law? Gauss's law is just another way of expressing Coulomb's law. Okay? It's also a more convenient way of calculating the electric fields of some, not a given charge distribution, of some special types of charge distributions. You know, charge distributions that have symmetry. That's what Gauss's law is all about. Okay, it involves the idea of the electric flux that we covered before. But, you know, very important, we are talking about the electric, we are talking about the electric flux through a closed 3D closed surface in the 3D space. It's not just an open surface, but a closed surface. Keep that in mind. Okay, let's go back to our illustrations here. Gauss's law right in here. Recall that last time, right? We calculated what was the flux, the electric flux through this surface, which by the way is an open surface. It's a planar surface. It's not a closed surface. So why did we do that? Because I want to give an example of how to calculate the electric flux through the simplest of all surfaces, right? That's why I did that. Here go. Here we have an open surface as well. Here we have another open surface. Here we have another open surface. It's a planar surface that's open. It's not closed. It's not completely closed. And now here we have the situation of a closed surface. It's a spherical closed surface. Okay? And then we can come up with other closed surfaces, not just spherical closed surfaces, but we can come up with a cylindrical closed surface. Okay? And those are the two types of surface that we are going to use to solve problems involving the electric field and Gauss's law. And like I mentioned before, it is possible to calculate the flux through this surface, right? The electric flux through this closed surface. It is possible, okay? What is not possible is to calculate the electric field through this specific surface that's not centered at the charge. I mentioned that before, right? So keep that in mind, okay? And I want to emphasize that here in the notes. Let's write that down. It is possible. Keep in mind that it is possible to calculate the efflux through an imaginary surface, imaginary closed surface, imaginary surface. Let's put it in a different way here. An imaginary surface that encloses, right, a given charge distribution. This is possible to do. Given charge distribution. Okay. What is not possible to do? Keep in mind the following. Keep in mind the following. Here you go. Let's organize here. One, it is possible to calculate the electric flux through an imaginary surface that encloses a given charge distribution, whether the closed surface is centered or not, whether the center here you go, of the closed surface is centered or not with respect to the charge distribution. This one is possible. Okay. It is also possible to determine the electric field on the surface of this imaginary surface. Surface being repeated twice, right? To determine the electric field distribution. Okay, well, let's put it this way. Around, right, this imaginary surface, if it is centered at, it's also possible to determine the electric field distribution around a point charge, right? Using Gauss's law, provided this imaginary surface is centered at the point charge. Okay? It's also possible to determine the electric field distribution around the point charge using Gauss's law, provided, right, this imaginary is centered at the point charge. However, what is not possible is to determine the electric field distribution around a point charge. Let me copy everything here. Around a point charge using Gauss's law if this imaginary surface is not centered at the point charge. Okay? And let me see if I copy and paste. Yeah, here you go. I copy and paste, right? So we already talked about that. But I want to emphasize that. So you understand the importance of having a symmetric surface around your charge distribution, okay? And what is the Gauss's law? I presume I also, yeah, that's Gauss's law. Here you go. So Gauss's law can be mathematical form of Gauss's law. Mathematical form of Gauss's law. That's the one. The electric flux through a closed surface is equal to this quantity that you see here. But don't forget, it's the closed surface, right? It's the charge enclosed by the surface. Okay? It can be rewritten in a different way. Okay, and the other way that can be written is like that. Epsilon. Yeah. Epsilon naught, and then I can erase this constant that goes here. Okay, epsilon naught is a dielectric constant of the vacuum. It has and don't forget, because of this relationship, right? You can deduce from this relationship that epsilon naught is going to be given by the inverse of 1 for pi k. You have a unit that's different. That's the inverse of the unit of k. The unit of epsilon naught is the inverse of the unit of k. Like that, right? And I'm going to put it here. The number 4 pi doesn't have any units whatsoever. The unit of the number 4 pi is 1, right? So that's the unit of epsilon naught. Every now and then you're going to see epsilon naught in the place of k, okay? Just for convenience purposes. And then we're going to do some examples, but before we do some examples, here you go. Use Gauss's law to find out the electric flux going through this surface, okay? Cannot use Gauss's law to determine, here you go, the electric field, okay, of this problem. You cannot determine the electric field, but you can determine the electric flux. That's the difference. You can determine the electric field, but you cannot determine the electric flux. If here is plus Q and here is minus Q, you just use Gauss's law to find out the you can use Gauss' law to find out the electric flux through this enclosed surface. Let's see here. Plus Q, right? Let's say this is one plus Q. And this one is minus Q. Like that. Plus Q and minus Q. In this specific case, the electric flux through this closed surface is going to be zero, right? But you cannot say anything about the electric field through this surface. You cannot say anything about the electric field through the surface because there is no symmetry in this configuration that you see right in here. Okay? That's what I mean by you can determine the electric flux through the enclosed surface. Okay, it's easier to determine the electric flux through an enclosed surface than to determine the electric field around the same surface. Okay, so let's take a look at the Gauss's law applied to the electric field of a point charge. You already know that what the electric field of a point charge is, right? You already know that. So example, so let us now use Gauss's law to find the electric field, E field distribution around the electric field of some charge distribution, some charge distributions. Okay? The first one, the easiest of all one, the easiest of them is the E field of a point charge, But I want you already know what's the E field of a point charge, right? But I want you to determine the electric field of a point charge, assuming that you do not know the Coulomb's law, okay? You already know that the E field of a point charge is given by the Coulomb's law. Coulomb's law, and I'm going to spell out Coulomb's law right in here. Coulomb's law for the electric field. K Q over R squared. Oops, I didn't put Q here. Q, right? Over R squared. This is way of a point charge, Q. However, now we will use Gauss's law. Now we use this Gauss's law to find the same expression, assuming that we don't we'll use to find the electric field, right? The electric field, assuming that we don't know the Coulomb's law for the electric field. We're just going to use some arguments of symmetry, okay? Just by using some arguments of symmetry, okay? That's what we're going to do. So here we go. Let's go get it. Here we go. We have here the equation, right? We have a point charge. Here you go. Here's my point charge. Point charge Q is a positive point charge. And I have to come up with my x-axis. Every problem in physics must have the x and y-axis. And we already know that for a positive charge. So let's write down what we know, right? What we can use, what's the knowledge that we can use, and what's the knowledge we cannot use. Okay? Solution. And I'm going to also Q greater than 0. Q greater than 0. Solution. Notice that we cannot use the Coulomb's law. Coulomb's law to solve this problem, right? Comma. But we can use the following. 1. Positive charges are sources of electric field. Okay? We know that. That we can use. Okay, so what does it mean? It means that the electric field radiates away from the electric charge. In the next step of Gauss's law, what do we have to do? We have to come up with a surface, a closed surface that encloses this charge, but on the top of that, you know, the whole set, the charge and the surface must have some symmetry with respect to each other. Okay, and the simple symmetry that we are going to have is that of a sphere which has a center, which center coincide with the position of the electric charge. Okay, a point is just a very infinitely small sphere, right? Can you think of can you think of it like that? A point is just an infinitely small sphere. Okay. And if we draw a sphere around this point, we are going to have a symmetric problem, provided the center of the sphere is at the position of the point charge. Okay. So next, positive charges are source of E field. For this reason, okay, E fields radiate away from the charge. Okay? Because a point charge is an infinitely small sphere, right? Comma. We can draw a larger sphere around this charge, around centered in the charge, right? In this charge, larger sphere, or like here you go, of radius r, centered at this charge, and adopted as our symmetric closed surface. Okay. And we already have it. Let's see if I put R. I didn't put R there. Let me put R there. So you know that this sphere has a radius R. I'm gonna change the thickness of this guy as well. The weight, yeah. Right like that. R. lowercase. Here you go. Like that. Sphere of radius r. In the next thing, okay, here you go. We recognize that the electric field is perpendicular, is normal to this imaginary surface, right? Here you go. Let me put this way here. Just another slide. We recognize that this imaginary surface is normal to the E field, like that. Is normal to the E field. And I'm going to draw a line that represents a plane, right? A plane tangent to the spherical surface. Okay, and I'm going to indicate that plane tangent to the surface and perpendicular to the E field. Let's write it down. Plane tangent to the surface and perpendicular to the E field. And I want to make it smaller so it can fit nicely here, but not too small, right? Otherwise you won't be able to read it. Plane tangent to the surface, to the imaginary surface. I don't want a narrow. I want this one here. Here you go. Here you go. Plane tangent to the surface, the perpendicular to the E field. Positive charges are source of electric fields. We can draw a larger sphere of radius r, centered and adopt it as a symmetric closed surface. What else? We recognize that the E field is normal to the Gaussian surface. Normal to the Gaussian surface. 4. We identify, next what we're going to do, we identify the area vector of this surface. Okay, area vector of the surface. We need the area vector we're going to need that to calculate the electric flux. Okay, we must also identify the area vector of the surface to calculate the electric flux. The electric flux depends on the area vector. And that's, and what we usually do, the area vector is going to be always normal to the surface as well, and pointing away from the curved surface. Okay? So here you go. The area vector is going to also be normal to the surface, but it will also point away from the curved surface. This area vector just like the E field, is also normal to the surface and points away from the center, the center of curvature. That's the better way of expressing it. From the center of curvature of the surface. Okay? The center of curvature of the surface is right here in the middle. So this area vector must point away from the surface, from the center of curvature. Note 6. Note that the area vector and the E field are parallel to each other, right? They are parallel to each other. And this is exactly now when we start calculating the electric flux. Okay? So the electric flux, remember the electric flux is E A cosine of the angle between E and A. Okay, cosine of the angle between E and A. And I'm gonna write down here the E and A vectors, right? Vectors. Here you go, E and A vectors. And don't forget the second, the other step there. What I want to do, I want to put in a different line so the line doesn't become too big, right?
Eu tenho o código.
So here you go. Don't forget, A here is the area of the closed surface, okay? But let's solve this case here because E and A are parallel to each other. So we are talking about an angle of 0 degrees. If we are talking about an angle of 0 degrees, the cosine of 0 degrees is going to be 1. And we reduce to this expression electric field times A. I do not know what E is, okay? I want to find E. Remember, right here, we are not allowed to use Coulomb's law. No, we are solving this problem assuming that we do not know Coulomb's law. We do not know this law right in here. Okay? But we do know what the area is. We do know what the area of the closed surface is. The area of the closed surface is what? 4 pi r squared. Right? 4 pi r squared. And now this 4 pi r squared times E must be equal to the right side of Gauss's law. Right? Here you go. I'm going to just repeat what I have here at the top, but I want you to be reminded, right, that we still have this term on the right side. The Q enclosed is nothing but Q itself. Okay, total Q. And look what we get, 4 pi cancels out with 4 pi. And we end up with what? We end up with exactly the Coulomb's law. Right? And here is the expression for the Coulomb's law, which was obtained using Gauss's law. That's the simplest problem of Gauss's law that you're going to see out there. The simplest example of Gauss's law that you're going to see out there. And now we're going to do some other example so you can become familiar with that. That's example number 2. What time is that? 3:24. That's plenty of time before our first break, right? Now example 2. To find the electric field of a spherical shell uniformly charged. See, there's a symmetric problem. Uniformly charged, and the shell has a radius r and charge q. Okay, so how do we illustrate something like that? Uniformly charged sphere. Here you go. Here's the sphere. The sphere with charge q. The sphere, let's say, is positively charged, huh? And it has a radius r. I want to do the following. Here you go. I want to do like that. Yeah. Play the movie, right? I like to do that. Here you go. A sphere, a shell, a spherical shell, very thin walls, radius r, positively charged, charge q. Oh, no, not what I want. I want that. Right, next. Right, next. Here you go. Yeah, now I don't need that. And then I'm going to put the x-axis and the y-axis. Play the movie, right? Let's play the movie, right? Let's see. Yeah, it's okay. Well, just to be consistent, right? Here you go. X-axis, y-axis, right? And now we are going to apply Gauss's law. Find the electric field both inside and outside this electric shell. Okay? You have a uniform charge distribution, and we have a sphere. Consequently, this problem has symmetry with respect to the center of the sphere. So we can construct a imaginary surface, Gaussian surface, on the inside of this spherical shell. And this Gaussian surface has a radius lowercase r. Don't forget my spherical shell has a radius r, right? And I'm gonna put it here. You go, capital R. Capital R here. Here it's gonna be 0. Oops. And this one right in here, minus R. Minus R. And now that you have plus R and minus R there, I no longer need that thing here, right? I no longer need that. When I put a y-axis, I will need the same thing. Plus R at the top, minus R at the bottom. And here is my imaginary sphere, my Gaussian sphere, lowercase r. And now we're going to use what's the amount of charge that's inside this sphere, a small sphere, right? You have to ask yourself, what's the amount of charge enclosed by this sphere? Okay? Think about that. That should be obvious, right? there are no charge whatsoever inside here. So when you write Gauss's law, you should write exactly what's written here. The surface is enclosing zero charge for this specific problem. Let's say radius A. Next, we will use Gauss's law to find the electric field of spherical shell inside and outside a spherical shell, uniformly charged of radius r and charge q. Okay, inside the shell. So we do exactly what we did before, right? The electric field inside the electric flux of the closed surface is going to be E times A. We already know that A is parallel to E. And we also know that A is not zero. We do know that A is 4 pi r squared, right? And since this number here is a non-zero number, this number here must be equal to zero, right? And now we can solve this problem, and we find out that inside the shell, the electric field is going to be zero. And you do the same thing for a region outside. We repeat the same thing for a region outside the shell. Okay? But now, instead of having a charge equal to zero, the charge is not going to be equal to zero. The charge is going to be equal to Q. And let's take a look outside, right? Here you go. Here's the Gaussian surface outside the sphere, the spherical shell. We also know that because of the symmetry of this problem, that the electric field of this spherical shell must point away from the shell itself. Also, because the concentration of charges anywhere along the surface is uniform, this electric field must be perpendicular, must be normal to the surface. Okay, and you can play, let's say find the electric field here at this spot, for instance, right? The electric field here at this spot is going to be away if you get the infinitesimal charge that you have here. But then the contribution of those charges here and there are going to cancel in this direction, perpendicular to the normal direction. Okay. So here you go. Outside the shell. 1, because of the symmetry of the because the charge distribution is positive, Q greater than 0. Yeah, greater than 0. Come on. The field must point away from the spherical shell. 2, what else? Because of the symmetry of the problem, the field must be normal to the spherical surface. In other words, The field must be radial, in the radial direction, must be in the radial direction. Okay, and that what we have right in here in this problem. The field is in the radial direction. And now we can finally finish the problem. Just like before, right? The area vector is going to be parallel to the electric field. You go. 3, because of the symmetry of the problem, we must use a spherical Gaussian surface, right? 4, surface. Like before, the electric field is parallel to the area vector. Okay? It's parallel to the area vector. And now we can finish writing down the problem. Here you go. 4kq, right? We have to have 4kq here. EA, there's no cosine in there because the area vector is parallel to the electric field. Here you go. 4kq. And 4 pi, cancel out with 4 pi. And the electric field, AQ over R is, oh, nope, over R squared, like that. And then, so notice that the spherical shell, the electric field of the spherical shell behaves just like, notice that the electric field outside the spherical shell behaves in the same way as the E field of a point charge. Okay. Outside the shell, here you go, R greater than 0. R, no, not 0, sorry. Less than big R, right? Not greater than 0, is greater than big R. So those are the two simplest problems that you're going to see for the Gaussian, for Gauss's law. There are others. Let me cover, we can here write in conclusion, right? How do we write the solution, right? Mathematically, we write like that. E is equal to 0 for R less than big R. E equal to that thing here for R greater or equal than big R. The next example is the example of the uniform electric field. Okay, find the electric field of a very large plate, flat plate, of uniform charge density. If the charge density is not uniform, then the problem is more difficult to solve. Okay? So let's stick to uniform charge density. And maybe Gauss's law cannot even be used to solve the problem. Net charge, the plate has a net charge Q greater than 0 in an area A. Okay? Don't forget, it's a very large. Yeah, let's put it this way, very large. No need to worry about the edge effects. If the plate, is small, you have those edge effects that we discussed before, right? In the lab. Let's take a look here at the problem. Let's see this one, uniform charges. We don't want to do that. Yeah, here you go, uniformly. Do you want to do that? No, this one requires, we don't want to do that. Uniformly charged sphere, that requires some calculus. We're going to skip that. Let's see. This is the linear charge density, right? Where is the plate? Uniformly charged cylinder. Okay, that should be the plate. Okay. Infinitely large planar surface instead of infinitely large, very large planar surface. Right? Very large planar surface. So uniformly charged. Here you go. The situation is like that. We have a planar surface that's very large, and we play a little bit with this plate to find out qualitatively how the electric field is going to look like. And the way it's going to look like is going to be something like that, right? Find out qualitatively or how the electric field is going to look at this point right in here. Okay, here we're going to have a contribution of this middle of the plate, just like we did before, right? Field is going to point in this direction. And then the upper half is going to contribute an electric field in this direction, and the lower half is going to contribute an electric field in this direction. Because of the symmetry of the problem, the vertical components of those two fields here is going to cancel out. Okay? It's going to cancel out, and then you're going to have a somewhat uniform electric field distribution, both to the right and to the left. Okay? That you already know because we covered before in a qualitative sense, right? But now we are going to use not just these qualitative ideas, but also a more quantitative idea, which is Gauss's law. How do you find out the strengths of this electric field? We do know that it's uniform, but how do we find the strengths of the electric field? Okay. 342, you're almost there, right? Can I finish that in the next few minutes? Let's see here. One, because Q, let's try to finish. Q greater than 0, the field must point away from the plate. 2, because the plate is very large, right, comma, its electric field must point along the horizontal direction. Not just away, but also along the horizontal direction. I still do not know if the field is uniform or not, okay? Gauss's law is going to tell us whether the field is uniform or not. Because the flat, let's see. Because of the symmetry of the flat plate, we can use a cylindrical Gaussian surface, a closed, can use a closed cylindrical Gaussian surface enclosing a small area of the plate. Okay, here you go. And that's the cylindrical surface I'm talking about. That's my Gaussian surface. Okay, and it has 3 different surfaces, right? you have the cylindrical surface per se, right? In which the area vector points in the vertical direction. In the radial, not the vertical direction, but in the radial direction. I call it the radial direction. Okay? In the radial direction. We have this cap here. This is surface number 1. The area vector points to the right. And you have the other cap here on the other side, in which the area vector points to the left. Okay? Now take a look here. Those are the electric fields, right? Those blue arrows are the electric field. Those blue areas are the electric field. Let me put another electric field here. Yeah, I already put it here, right? Surface 1, surface 2. Right? So now we are going to use a different type of surface to find out the electric field of this charge distribution. How do we do that? Let's not forget that the electric flux if I can write it down, this closed Gaussian surface is made up of 3 open surfaces, right? Let me put a period here. 1, the cylindrical one, and the 2 caps at the end of the cylindrical one. Okay, so Gauss's law looks like something like that, you know? The electric flux through the whole closed surface is going to be the electric flux through the surface number 1 plus the electric flux through the surface number 2, the electric flux through the surface number 3, okay? And we are going to calculate those, each one separately. Let's do separately. Here you go. The electric flux through the surface number 1 is going to be equal to, look at here, surface number 1, electric field is parallel to the area vector, right? So we can state that because they are parallel to each other, we can write down as being E1, right, times A prime. Let's call that area A prime. And we get something similar for the surface number 2. E2 times A prime. We do not know if those 2 electric fields are the same. You're going to see that they are the same, okay? What about the phi 3? Phi 3 is the easiest of all, okay? The area vector is perpendicular to the electric field. Consequently, the angle is 90 degrees. Since the angle is 90 degrees and the cosine of 90 degrees is 0, the electric flux through the third surface must be 0. Okay? And now we have this relationship right in here. Okay? We have this relationship right in here. Let's go another step. E1 plus E2 multiplied by A prime, right? That's what we get here. We do not need the 0 anymore. the area is the same. The area to the right is the same as the area to the left of the plate. And now we also recognize, now we must recognize that E1 and E2 must be equal because of what? They must be equal. Because I chose my cylinder in such a way that this distance here is equal to this distance here. Okay? Must be equal because each half of the, let's see, because each cap of the cylinder are at the same distance. Okay? If you are at the same distance from your sources, then the electric field intensity must be the same. So here you go. E1 or, right? Oops. Oh gosh, what did I do here? Just want to copy. Or, here you go. E1 must be equal to E2, which must be equal to E. Okay? And now we have one more important result to write down here. E1 plus E2 is E plus E. E plus E is equal to 2E. E plus E is 2E. And A prime, the area of this cap here, must be given in terms of its radius. Okay, here you go. And we have right in here, here you go, the radius. I'm looking from the top, right? The area of the circumference is going to be 4 pi, pi r squared, not 4 pi, pi r squared, radius lowercase r. I'm doing lowercase r because it's the genetic r. Okay. And we're getting there, almost there. Don't forget, we have the right side of the equation that we must not forget about it. The right side of the equation is this one here. Huh? Like that. We do not know what E is. This Q enclosed, okay, can be rewritten in a different way. Okay. We do know that the charge distribution is uniform. And what do we mean by uniform? It means that delta Q, what does it mean? It means that delta Q, over delta A, right? Constant anywhere, same value anywhere throughout the surface. That's what it means. Okay? So it also means that since the plate has a net charge Q and a net area A, okay, it means that delta Q over delta A is going to be Q over A as well. Okay? And the amount of charge in this area here that you see that R square right in here that I mentioned to you? It's kind of hidden, right? Yeah, let's see if I can make it more obvious. Make it bold-faced. and even reddish color, and I'm gonna make it larger too. I didn't see it the first time. That's why I'm doing that now. And let me do this arrow. Oh, this arrow. Oh gosh. I'm gonna make this arrow thicker as well, so we can see it more easily. Oh gosh, let's try it again. Does not let me do. Let me try a third time. If it doesn't work, I'll give up. Only 3 times, right? Okay, shape outline. Yeah, wait. Can make thicker. Yeah, good. And I'm gonna make this arrow also red. Yeah, so it's whoa. Oh, I hate that. Okay, I give up. I'll leave the R like that. Okay, so here you go. Delta A is exactly this area here that we're talking about. Is a fraction of the total area of my plate, okay? So we can write that down, that the charge enclosed by that Gaussian surface is Q over A times delta A. Delta A should be pi r square, and I have it right here. It's the same pi r square, all right? This delta Q is my Q enclosed. Delta Q is also my Q enclosed. And finally, we have that Q enclosed is Q over A pi r square. Q over A pi r square. I can erase that from here. We're almost done. Almost done. Okay. Very soon we're gonna go for our break. Here you go, using the previous result for the electric field. Okay, here is Gauss's law. Here we are calculating the amount of charge that is enclosed by the surface, right? Another one, Q encloses this one. Place right in here. And look, something interesting happens. Look what's happening here. This pi r square cancel with this pi r square. We also have that this 2 cancel here with this 4, right? Yeah. And what else? Note see that 2 is constant. Pi is also a constant. K is also a constant. Q is the net charge of the plate, okay? A is the area of the plate, and they are all constants. What does it mean? It means the above result states that the electric field does not change with the distance to the plate, okay? The E field is uniform. That's what it means, is uniform or has the same value everywhere. Okay? This is what we call a uniform everywhere in space. This is what we call a uniform E field. Okay? This what you see right in here too, there's a name for that. It's called surface density of charges, okay? The amount of charge divided by the amount of area. Surface charge density we represent by the letter sigma, okay? Surface charge density. And that's how we determine that the large plate, uniformly charged large plate, is uniform. We use Gauss's law. It's a long procedure, but it works very well. Okay. So now it's 11 o'clock right now. Let's take a break, right? Break 11 a.m. to 11:15. Do you have any questions before you go to the break? Okay, no questions. Okay, so I see you in 15 minutes. Okay, we're back here, and that's how we, work. That's how we use Gauss's law to calculate different charge distributions. Okay, and we can go another step here. Okay, we right now what we calculated right now. What we did right now was the E field of a single plate, right? That's what we calculated. We calculate the electric field of this single charged plate, the field to the right and the field to the left. Because the plate is very large, the electric field is going to be uniform throughout the whole space. Okay? And now that, and we can do the same thing for the negative charge, okay? We can do the same thing for the negative charge. And the step by step is going to be exactly the same. The only difference is that the fields are going to point towards the plate, right? Let's write that down. The same thing. The same thing can be done for a negatively charged plate. The step by steps are the same. The step by step are the same. Okay. Step by step are the same. We can now find out what is the field when we add a second plate with an opposite sign, right? We can now find out what is the E field when we add a second plate next to the other with an opposite sign. And I can illustrate that here. Remember, positive plate, and here you go. Positive plate. That's the positive plate, right? Field away. That's the negative plate. Field towards. Now what I'm going to do? I'm going to get my positive plate. I'm going to shift it a little bit to the right. And I'm going to add the negative plate to the left of the positive plate, right? Positive plate, negative plate. When I place this negative plate next to the positive plate, we have this superposition of electric fields in space. Look what happened, folks. It's very easy, right, to visualize it. The difficult part was to calculate this field here. That was the difficult part. This was the difficult part. This was the difficult part, right? But now, if we combine those two plates like we do have in many electric devices, electric and electronic devices, we can realize that the field outside the volume of those two plates are going to cancel out. Do you see that what's happening? The field is uniform. The electric field of the positive charge is to the right. The electric field of the negative charge on this side is to the left. What happened? Those two cancel out. Those two fields cancel out. But in the volume between the plates, the field of each plate is going to reinforce the other field. Okay? And what we end up having is going to be something like that. A stronger field inside the volume, a much weaker field in the volume outside the two plates. Electric field equal to 0. Can you picture that? Okay? If and we can repeat the same thing, for two plates of the same sign. Okay, let's do that. It's gonna be, instead of and that was exactly the situation that we had in our first lab. The field, an intense field on the between the plates, and a field almost 0 on the outside of the plate. Okay, and I want you. Let me see. Let me copy, paste. Yeah, here you go. Now, what would the field look like if you had, instead of negative charges here, what would the field look like if you had positive charges here, right? What it would look like, okay? Let me erase everything here. Okay, I want you to think about that and what would look like if you understood how the superposition principle works. You should be able to solve this challenge. What would look like if you have two negative plates next to each other? Here you go. Like that. What? Here you go. Let me erase this guy here. Okay, so two different ways. Two other different configurations, right? You can use exactly the same procedure that I used here. Okay, you can use exactly the same procedure that I used here. Put one plate next to each other. Okay, and let me leave this way for now. Okay, and let's see here what I'm gonna do in the notes, right? What example? Another example, right? What is the E field distribution, right? Whenever we place a negative planar charge distribution next to a positive planar distribution, right? What's the E field distribution, right? Solution, already did that the solution for you, right? In between the plates, the field doubles, right? In between the plates. It's gonna be something like that. 4 pi k. Oh, 4 pi k. Okay. Which can also be rewritten, by the way, as sigma over, and just another way, epsilon naught. That same epsilon that I mentioned to you before. Okay. And here too, in that previous result, right, I can here write it as sigma over 2 epsilon naught. Okay. Notice that this field is half of the other one. Outside the volume, between the plates, the field is negligible, E equal to 0. Okay. Think about that. We're using, like I said, we're using just the superposition principle. Okay. Let me take a one minute break here. Okay, there's something going on here at home. I want to address it quickly, and I'll be back shortly. Just 1 or 2 minutes. Okay, I'm back. Good. So we have those examples of how to solve problems using Gauss's law. Okay. Let's take a look at the book. Now this one right in here, Gauss's law. That's how his, electric flux. See here, the electric flux. See, he's using a different notation, right? Q over epsilon naught. For pi k is the same thing. For pi k q, it is for the point charge distribution, Gauss's law. Here you go. See, he's using a summation, right? Depending how many surfaces do you have, you need the summation. For the point charge, you have just one term in the electric flux. For the spherical charge, we had just one term, but for the planar charge distribution, we had 3 different terms in the summation for the Gauss's law. Thin spherical shell, we did that. Okay, here you go. See the Gaussian surface inside the spherical shell, Gaussian surface outside the spherical shell. Parallel plate capacitor. This is exactly what we did, right? Gaussian surface. I don't like the way he did here. I don't think it makes sense. Many books, I believe they make this mistake. So I like to do it the way I did to ensure logic, right? The proper logic process. Here you go. Let's see if they have another one. Yeah, okay, so he did only those 2, and that's what we're going to do as well, just those 2. Here, the Gaussian surface enclosing the charge, okay? Like I said, you can calculate the flux, the total flux across the surface, but you wouldn't be able to calculate the electric field, okay? Here, the total flux across the surface is the net sum of those charges, which is going to be 2, right? Twice twice 2 microcoulombs plus 1 cancel out this -1, 2 microcoulombs times 4 pi k, right? Here in this case, it would be 2 microcoulombs times 4 pi k. And here would be like 4 pi k Q1 plus Q2. You can calculate the flux, but you wouldn't be able to calculate the electric field because this problem does not have symmetry. Okay, and that's what we have for this chapter 18. Copy and paste. Keep track, right? Everything that's bold-faced, we covered. What I want to do is to cover this section here, capacitors and dielectrics. It's very difficult to emphasize the importance of a capacitor, okay? It's very difficult to emphasize. So you gotta learn about it. It's a very important device in electricity and electronics. I didn't like this when I started taking this course back in undergraduate school in Brazil. I didn't like electricity, so I didn't pay much attention to it. And I didn't have a clue what a capacitor was, even though I went through the course, I passed it successfully, right? And I never liked it, this topic on electricity and electronics too, until the day I couldn't get my circuits together at NASA when I was working there at NASA. And because of that, I couldn't reduce my technology to practice at that time. It's a shame. If I knew then what I know now, right, history would have been much different for my technology. Okay, so I want you to understand that what we're going to discuss right now is very important. It's tremendously important. Okay, and because it's going to help you to put together electric and electronic circuits whenever you start doing research, whenever you start to exercise your profession, hopefully in the lab. Okay, so but before we start talking about capacitors, I'm going to tell you something. There are 4. Okay, you already know that there are 3 core concepts in physics, right? You already know that. The basic quantities, right? The basic quantities, the primary definitions, and the laws of physics, right? That's how physics is put together. That's how physics is put together. In addition to that, there are also only 4 basic devices in electricity and magnetism, okay, / electronics. I'm talking about devices. Every device that we have, our cell phone, our TV, our screens, they are all built around those four basic devices. They are all cell phones, anything that's electronic. Okay, this keyboard that you have right here, you know, it has a bunch of those components right in here inside this keyboard. And even better, this keyboard, we can type in our keyboard because the keys of those keyboards, they are coupled to a series of capacitors, several capacitors, okay? Which is just one of the four basic devices in electricity and magnetism and electronics. And let's talk about those important basic devices, right? Basic devices in electricity and magnetism. The first one is the capacitor. It's the simplest of all, the one that was invented, the one that was first invented. And I'm going to tell you how a capacitor is put together very soon. Okay, hang in there. The other one is the resistor, which we're going to talk about later on. The other one is the inductor. And the fourth, we're going to talk about all those three. We're going to cover them all in our course. The one that we are not going to cover in the course is a device that was invented in the 20th century. Okay, those devices are, you know, they're old. The capacitor is an old device. We can take a look at their history. The resistor in a way is old too, the inductor, right? And then this other device that was invented only in the 20th century is the transistor. Have you heard of the transistor? Okay, have you heard of the transistor? Let's take a look at the capacitor. The capacitor was originally called the Leyden jar. Leyden jar, okay? At that time, here you go. History of the capacitor. Capacitor. Let's take a look at the Wikipedia. Okay, the history of the capacitor began in the 1740s. So it was in the 18th century with the invention of the Leyden jar. Remember I told you about that? An early device that stored electric charge in water-filled glass jars. Independently discovered by Ewald George von Kleist, right, and Peter van Muskenbroek, 1746, 1745. It allowed the accumulation of large electrical charge. Benjamin Franklin, hey, you know that, right? Famously used those jars to prove that lightning was electricity in 1752. Okay? Benjamin Franklin was almost killed by that experiment, right? He was a brave man who risked his life in pro of science. So, and here are a bunch of capacitors that are sold out there in the commerce. Okay. Key historical developments and evolution of materials. Early researchers discovered that the glass served as a dielectric material. And a dielectric material, what's a dielectric material? The electric material is an insulator. While the water and metal acted as conductors, okay? The term condenser was later coined, now rarely used in English, and was replaced by the term capacitor. Condenser was a synonym for capacitor. The unit of capacity, farad, was named after Michael Farad. Modern advancements, the 19th and 20th century saw the development of paper, electrolytic, and ceramic capacitors. I'm going to show you exactly how they look like. Well, all I want to do to show to you is the historical background of the capacitor. Okay, modern era. So the capacitors range from tiny components in electronics to large banks used for pulse power, with technologies evolving into electrolytic film and supercapacitors. Okay, so right now, right in here inside this keyboard of mine, there is a bunch of capacitors. Each key that you have here is attached to a capacitor. We use the capacitor to map which key we are depressing in the keyboard. And those capacitors are, again, used so the computer can identify what words you are writing in the computer, okay? The A keyboard is attached to a capacitor. The B key in the keyboard is attached to a capacitor, and so on. And like I said, capacitor is just one of the four main components in electricity and magnetism and electronics. If you want to understand electronics, if you want to understand electrical circuits, electronic circuits, you have to know about the capacitor and the other three components. That's why we covered them, okay? And we are done here, right? Let's see here. Yeah, I need the other. No. Illustration right in here. Electric potential and capacitors and dielectrics. Let me tell you what's the capacitor is a very simple device, okay? The simple devices are the most powerful ones. You know, we think about that we need something very complicated to revolutionize science. Don't think that you need something complicated. You need something very simple to revolutionize science. Something simple that can be used in many configurations, and the capacitor is one of them. It's such a simple device that we keep on saying, once we are taught about it, we keep on wondering, well, what the hell this thing is so important, right? But that's what science is all about. It's about inventing simple devices that can be used in multiple applications, okay? And the most generic capacitor is a piece of metal. Here you go, I have a piece of metal right in here. Next to another piece of metal. That's all. That's the most generic. It doesn't matter the configuration. One doesn't have to be exactly equal to the other, okay? It's just the most generic configuration of a capacitor is this one. Two pieces of metals next to each other. That's it. Okay? That's what capacitor. And then why is it so important? Well, it is important because it can store energy. That's why. It can store electrical energy that then, if properly used, if properly tapped into, can be used to power your devices. Okay? So here you go. At this very moment, what you see right in here is a capacitor that is uncharged. Two separate lumps of metal next to each other. Okay? And because this capacitor is uncharged, you cannot do any work with it whatsoever. You cannot do anything useful with it whatsoever. But it's still a useful device if you end up charging it. How do you charge it, right? Okay, here you go. I'm going to connect those two devices to something else that's going to allow me to charge each one separately. So let's say those two lumps of metals are separated by a distance d, okay? A distance d, and then I can apply a potential difference between them. And what do I mean by applying a potential difference between them? I can connect a battery to both of those lumps of metals. When we connect a battery between those two lumps of metals, one is going to become negatively charged and the other is going to be positively charged. Okay, and now that the capacitor is charged, it does have some energy here, some electrical energy that now can be used to do some important work. Okay, that's what a charged capacitor is. Opposite charge. Let me see. I'm gonna change opposite charge. Opposite charge. Okay, misspelled there. Let's write it down. Here you go. The most generic capacitor is made of two lumps of metal. Oh, and there is more, okay? Not just two lumps of metal separated by a dielectric material. That's very important. The capacitor, the two lumps of metals cannot be electrically connected with each other. Separated by two dielectric, by not by two, but by a single dielectric material. The dielectric material or electrical insulator, dielectric materials is synonym for electric insulator, okay? Is used to ensure that the charges in the lump of metals are not affected. Okay? That's the role of the dielectric material. Two lumps of metal separated by an electric insulator. So it can be two pieces of iron, okay? Sandwiching a piece of glass, for instance, okay? Which dielectric materials, right, can we use? Can we use to insulate these two lumps of metal, right? Almost any dielectric material, and we covered that before, right? We can use glass. We can use wood. We can use paper. We can use plastic. We can even use the air. The air is a dielectric material, etc. Deionized water is another good dielectric material. Deionized water. Deionized water is another good dielectric material that can be used to insulate the two charged metals, two charged lumps of metal. Okay? And that's exactly what we're doing in the manufacturing world, okay? Let's go back to our search here. We're going to go into Wikipedia. You're going to see different types of capacitors. They can be small or large, okay? Here you go. They have all sorts of configuration, all sorts of geometries. Here is a cylindrical capacitor. Here is a planar capacitor. Okay, here's a type of capacitor that's used in our radio to tune to radio stations. Okay, and many others, small and large. Okay. Now, another example, more specific example of a capacitor is the parallel plate capacitor. Now do you understand why I introduced you to the two plates? You know, here you go. The parallel plate capacitor is just like two plates, one positively charged, the other negatively charged. They are initially uncharged, right? Even though they're uncharged, they're still considered a capacitor. They are not in electrical contact with each other because we have some dielectric separating them. We have some electrical insulator material separating them. If you connect them with a wire, they stop being a capacitor. They cease to be a capacitor because once you charge a capacitor positively, the wire is going to make the capacitor become uncharged. You're going to waste electrical energy. Okay, so here you go. I'm charging the left plate, connecting the left plate with the negative polarity of my battery, and I'm going to charge the right plate. I'm going to connect the right plate to the positive polarity of my battery. When we do that, an electric field is created between those two plates. The electric field, and the uniform electric field that goes from the positive charge to the negative charge, right? Here's the change in voltage, delta V. That's one example of a type of capacitor that we have out there in the market. But we can also have a capacitor that's a spherical capacitor. We can use a spherical shell, metallic shell, that is concentric with another metallic shell, spherical shell. Here you go. Inner shell, outer shell. They must be separated by a dielectric again, okay? This volume in between them. Like, again, this dielectric can be air. This dielectric that fills the space between them can be air, can be deionized water, can be paper, can be wood, can be plastic, can be glass, and so on. Once you connect those two shells to the distinct polarity of a battery, the spherical shell is going to be charged, and you are going to have a charged capacitor. Here you go. Now it's charged, right? And when they are charged, what's going to happen? We are going to have an electric field that's going to point from the positive to the negative. And that's going to be our lab number 2, okay, folks? It's going to be not exactly that. It's going to be a similar configuration because this one is spherical shell. Okay. And here you go. The spherical shell capacitor. One end is going to be kept at 1 voltage. The other end is going to be kept at another voltage. Okay. So here you go. The electric field inside here is going to be 0, and you can find that out just by applying Gauss's law. There is no charge here in this volume. Consequently, the electric field is going to be 0. But the electric field in this middle region, in the sandwiched region, right, is not going to be 0. But the electric field outside is going to be 0 too. Why is that? Again, you got to apply your spherical Gaussian surface. And when we apply our spherical Gaussian surface, we discover that the net charge enclosed by the spherical Gaussian surface is 0. And if the flux ends up being 0, it means the electric field here in this outside region is going to be 0 as well. Okay? Can you picture that? Here you go, another configuration of the capacitor, the cylindrical shell capacitor. Concentric cylindrical shell capacitor. Here you go. And that's what is the configuration that we're going to use in our second lab. Okay, here you go. One is going to be charged. You know, which one is charged positively doesn't matter. Okay, can be whatever you want. The outer one can be positively charged, the inner one can be negatively charged. Okay, so here you go, negatively charged outer one. And here, what you see when you look from the ends of the cylindrical shell. Okay? There will be an electric field in this region. Electric field here, just like the spherical capacitor, okay? The electric field is going to be zero here inside. The electric field is going to be zero here outside, just like the spherical capacitor, okay? Just by applying Gauss's law. Cell as a capacitor. And by the way, you folks that are in biology, right? It's very important. Cells that we have in the animals, right? They work like a capacitor, by the way, okay? It's this organic material, but actually they do work like a capacitor. If you have a cell, here's the membrane of the cell. And on the inside of the cell, if you end up developing a charge distribution on the inside, you're going to attract opposite charges on the outside environment. And now that we have this charge distribution between the membrane of the cell, and the membrane of the cell is a dielectric material, now you're going to develop an electric field across this membrane, and this electric field is going to have some energy that the cell is going to use to perform some of its work, okay? So that's where the cells in our body get their energy from. They get their energy from the electric field. And like I said, a cell works just like a capacitor, okay? So here we go. Different dielectrics between the conductors of a capacitor. Did you get the idea? Okay, so let's write that down. Which dielectric material can we use to insulate these two lumps of metal? Okay, glass, wood, paper, right? So I already explained to you what is a capacitor, right? Two lumps of metal separated by a dielectric material. Let's say not two lumps of metal, but two lumps of conducting material, okay? Separated by a dielectric material. Separated by a dielectric. It doesn't have to be metal. It can be, you can have a capacitor made of salt water, for instance. Salt water is a conducting material, okay? Okay, there are all types of capacitor geometries, okay? One, the parallel plate capacitor. Two, the spherical capacitor with concentric shells, right? The cylindrical capacitor with concentric shells, and so on, and others. The limit is your imagination, okay? Like I said, can be the most generic geometry that you can get out there. Can be a lump of conducting material, two lumps of conducting material insulated to each other, electrically insulated to each other. What time is that? It's 12 noon already, huh? My goodness, we should take our break here, right? Let's take our break. Break at 12 noon to 12:15, right? Yeah. 12 noon to 12:15 p.m. and then we continue in the next 15 minutes. Any questions before you go into a break or break? No? Okay, I see you in 15 minutes. Back. Oops, close it. Let's see. Back here. Okay, so now that you have a good idea of what a capacitor is, okay, now that you have a good idea of what a capacitor is, right? We can, a qualitative idea, right? A good qualitative idea of what a capacitor is. We can start talking about numbers, right? And numbers, I mean equations, numbers or equations, right? Or equations. First, the qualitative idea, and then the quantitative idea. Okay, or equations. Let me get, yeah. Okay. So let's write that down. Capacitors and capacitance. And capacitance. Don't forget, right? The four important devices in electricity and magnetism. Capacitor is the first of them. If you want to know how any electronic device works, you have to understand about those four. In this course, we're going to cover only those three. These other one, transistors, are covered in a more advanced course. The guy who invented the transistor, by the way, is they won the Nobel Prize in physics. Okay, Bell Labs, researchers from the famous Bell Labs, Bell Lab that was dismantled. I was alive when Bell Labs still existed. Okay, I used to collaborate with people there at Bell Labs in Murray Hill, New Jersey, and Bell Labs won a bunch of Nobel Prizes. Okay, and those guys, one of the guys that invented the transistor used to work at the Bell Labs. I didn't know him, but I worked with some other people in the field of optical fibers, by the way. Okay, so let's talk about capacitors and capacitance, right? Okay, you already know what a capacitor is, and in order to quantify capacitor, here you go, let's write that down here. Capacitors are devices that are capable of storing electrical energy within them, right? Within them. In order, but don't forget the capacitor, forget the capacitor must be charged. To store any energy. Okay, and you charge the capacitor by connecting it to a battery. That's one possible way. There are other ways too. Okay. To quantify a capacitor, we define something that we call the capacitance of a capacitor. Okay? The capacitance of the capacitance. Let me show you something else too, okay? Whenever we are talking about electrical circuits, whenever we are talking about here, we use this symbol here to represent a capacitor, okay? A capacitor of fixed capacitance, of fixed capacitance value. Two parallel plates, okay? One end of the capacitor, let's say, one lead of the capacitance of the capacitor, another lead of the capacitor. And the symbols of our capacitor is that one that has the parallel plate, right? So we use the symbols capacitor as the symbol of any capacitor. Two plates can be in the vertical, can be in the horizontal, okay? We can draw that in the vertical, in the horizontal, whatever it is, okay? To quantify a capacitor, we define something that we call the capacitance. We call it its capacitance. Okay? And the capacitance can be written as is defined the capacitance. And the capacitance is defined according to the following equation. Here you go. That's the equation. The amount of charge divided by the electric potential difference. Do you remember that the way I drew the capacitor before? Let's go back there. This one here. No, it's not this one. It's the other one. Must be this one here. Initially, right? I drew this capacitor here. So if we divide Q by the electrical potential difference between those two capacitors, we obtain what we call the capacitance. Remember this definition. This definition is very important. Same thing here, right? If we know what's the charge, the amount of charge Q in terms of Coulomb, and divide by the electric potential difference, the voltage difference between those two plates, we get what we call the capacitance. This unit, the unit of the capacitance, here you go. Unit of the capacitance is the unit of the charge, of the electric charge, divided by the unit of the voltage, right? The unit of the electric charge is the Coulomb, and the unit of the voltage, I didn't discuss that here before, right? The unit of the voltage, remember that the unit of the voltage, how the voltage is defined? Is the electric potential, right? Is the electric potential energy divided by the charge. That's how the potential difference, the electric potential is defined. Is the electric potential energy divided by the amount of charge. Okay, and this unit shows up so frequently in physics. This unit here shows up so frequently in physics that we give it a name. We call it the volt. We call the volt, and we write it down as being the V, C divided by V. Okay? The unit has the same symbol for the voltage itself. Okay? Maybe we should put delta V there. Let's put delta V there. Yeah, let's put like that. That's the unit of capacitance, Coulomb. Oh, don't mix up the C for Coulomb, okay? The C here stands for Coulomb. This other C here stands for capacitance. You gotta be careful about that. Maybe I should even put a prime there to distinguish from each other, okay? Now, there's more. There's more. Okay, this unit, again, shows up so frequently in physics that we give it a name. We call it the farad and abbreviate by the letter F. Okay? Don't forget units of voltage, right? I'm gonna emphasize it here because I didn't mention to you before. Delta V is equal to the electric potential energy divided by the electric charge, right? The unit of voltage is equal to the unit of electric potential energy divided by the unit of charge, right? The unit of electric potential energy is the joule. The unit of charge is the coulomb. And J divided by C is equal to the volts. The volt, which is abbreviated by the letter V. And the unit of capacitance is the unit of coulomb. Oh, let's put capacitance here with C prime. Yeah. Divide by the unit of voltage. This unit shows up so frequently that we call it the farad and abbreviated by farad, by F, by the letter F. So now we can come up with a very simple example, a straightforward example. Okay, not every physics problem is as straightforward as this one. This example use just the very definition of capacitance. A capacitor can hold a maximum voltage of 35 volts. Its capacitance is known to be 4,700 microfarad. What's the maximum charge that this capacitor can carry? Maximum voltage, right? And he's asking maximum electric charge. Let's take a look here. Here you go. Let's take a look here at this definition, capacitance, right? So here you go, maximum charge. Oh, no, he doesn't like it. Here you go, gotta trick him. Maximum, oh, again. What the heck's going on here? Maximum voltage, maximum charge. We want to know the maximum charge. We know that the maximum voltage is 35 volts. We also know the capacitance, right? So it's a very simple problem, straightforward problem that ends up being equal to, oh, no, C prime times delta V max. Do you see that the charge is directly proportional to the voltage? Here you go. All you have to do is substitute the numerical values and calculate it, right? And calculate. Let me see, did I do it right? Capacitance. Oh, no, I did. No, I did it right. Yeah, I did it right. Yeah. No matter what the voltage or charge you use, the capacitance is always gonna be the same. Okay. There you go. No matter what the charge or voltage you use in a capacitor, its capacitance will always be the same. provided, okay, provided you don't exceed the maximum charge or voltage. Provide you don't exceed the maximum provided, right in here. You don't exceed the maximum charge or voltage, okay? Always be the same. It's the capacitance is a constant of a given capacitor, irrespective its voltage or charge. But don't forget, you cannot exceed the maximum value of the charger and the voltage. So here you go, Qmax. Now you go ahead and put the numbers there. Here is going to be 4,700 microfarad. 4,700 microfarad is 4.7 millifarad, by the way. The maximum voltage is 35 volts. You do this math and then you get right? In coulombs. You get whatever in coulombs. And now we are going to obtain the capacitance of a parallel plate capacitor in terms of generic values, okay? Variables, in terms of the generic variables. Now that we have the definition of capacitance, okay, now that we have the very definition of capacitance, comma, we can find an equation for the capacitance for the capacitance of different types of capacitors. Okay? And the different type of capacitor, which one? The parallel plate capacitor. The parallel plate capacitor, comma, the spherical capacitor, the cylindrical capacitor. In both cases, we are talking about concentric, right? Let's start with the parallel plate capacitor. Let's start with the parallel plate capacitor. Okay? Consider a parallel plate capacitor with charge Q, area A, and separation between plates D. Okay? Find an equation for its capacitance. Example. Solution. Solution. So we go ahead and use the definition of capacitance that's here. Okay. Is the amount of charge. Doesn't have to be the maximum amount of charge, it's just the amount of charge divided by the electric potential difference. I'm just gonna, let's see, I gotta here write that. Delta V, okay? Even better, V for voltage. Okay? Okay, you do know that the field inside a parallel plate capacitor is uniform, right? You do know that, right? Remember that? The electric field. Here you go. E is what? Sigma over epsilon naught. Over epsilon naught, like that. And sigma is what? Sigma is charge divided by area of the capacitor. Right? Given, right? Given. This one is given, right? And this one is a constant. Now, we must obtain an equation for the voltage between the two plates of the capacitor. Okay? Well, I discussed before with you, right? I discussed before with you that the voltage is directly proportional to the electric field. Remember that? Electric field, right? So here you go. In the case of a parallel plate capacitor, the voltage is going to be, delta V over delta X. Delta X. Okay? So the delta V that I have here, let's put delta V here. Okay? Let's put delta V. I prefer delta V because we do not mix up this V with the unit. That's why I prefer delta V. Okay? And delta X is the separation between the two plates. Okay? And the separation between the two plates, you go. Let's substitute this one here for the E. The separation between the two plates is going to be the distance D. That is given out there. And now we can, I'm going to simplify this equation. A goes downstairs. Yeah, A goes downstairs. Now we do not need A anymore. We write delta V here. Delta V is Q over A epsilon naught times D, right? Erase, here you go. And now my delta V is given in terms of known parameters, Q, A, D, and epsilon naught. We can substitute writing here for the capacitance of the generic capacitance, right? I'm going to substitute delta V right in here, and look what the interesting thing that happens. The capacitance does not depend on the charge at all. Does not depend on charge at all because the voltage will most of the time be proportional to the charge, folks. Okay? So every time that you have a capacitor out there, the capacitance is going to be independent of the charge. And the capacitance is going to be dependent only on the geometrical features of the capacitor. What happened here? Of the capacitor. Let's see what happened here. Huh. I don't know what it's doing here. Strange. Okay, this guy here goes upstairs. we usually write this equation with an epsilon naught here in front, like that. Okay? Note C that the capacitance depends only on the geometrical parameters of the capacitor. Its area in this case, right? In this case, its area and separation between plates, between the plates. Okay? Plus, of course, the electrical constant. Plus the electrical constant. And you get, by the way, you get exactly the same thing for the spherical and cylindrical capacitors. You get exactly the same thing for the spherical and cylindrical capacitors. Let's do for the spherical capacitor. Find, here you go. Find is another example. Find the capacitance of a spherical concentric capacitor, a spherically concentric capacitor of inner radius A and outer radius B. Do I need anything else? Right? Now we don't need anything else. I don't even need to tell you what's the charge of the capacitor, because remember, the charge is going to cancel out. The voltage is going to be proportional to the charge, and the charge in the definition of the capacitor will cancel out with the charge in the voltage. That's all you need. Okay? So here you go. Now we got to go back to that here you go. Spherical capacitor, right? Remember the spherical capacitor that we have right in here? Okay. In the case of the parallel plate capacitor, delta V here is going to be equal to the electric field times the separation between those two plates. Okay. In the case of the spherical capacitor, the voltage is going to be slightly different because it's going to be the voltage of a point charge, right? Remember that? It's going to be the voltage of a point charge. And because of the geometrical symmetry of the problem. Okay, so here you go. This surface right here is going to be kept at a voltage that's going to be equal to that of a point charge, KQ divided by B. That's the distance from the center. And this other spherical surface is going to be kept at a voltage also given by that of a point charge, KQ divided by the distance A. Make sense? Okay, so here you go. Solution. We start with the definition. What time is that? That's 12:45, right? Yeah, 12:45, 44. We have 6 more minutes to go. That's the definition we want. The potential difference is going to be the potential difference of the inner surface minus the potential difference of the outer surface. okay? Because we do have, and by the way, what we have here is in reality the magnitude, okay? It doesn't matter. It's always going to be the magnitude. Think in terms of magnitudes always. For the capacitance. Okay, no, magnitude is here, sorry. Let me fix that. Magnitude is in the formula. Here too, the Q, because the Q can be negative, right? The magnitude goes right in here. Delta V doesn't have the magnitude here. Okay? The VA is going to be given by what? The point charge, right? K Q divided by A. KQ divided by B, right? Note, see that we have common terms. KQ are common terms. I'm going to put my multiplication here. 1 divided by A minus 1 divided by B. Right? Here you go. And now we can start solving this problem. The only put right in here, okay? Remember, it has to be the magnitude, right? Let's see here. I put the magnitude right in here. Yeah, not this one right in here. Good. K is always positive. So we can take it out. We can keep the magnitude of Q outside as well. And we can keep the magnitude of this term as well. Magnitude of Q cancels out with magnitude of Q, right? You're always going to have something like that. And here you go. Cancel, cancel. And again, you got exactly what I told you before. The capacitance depends only on the geometric parameters of your device. The inner radius of the inner shell and the radius of the outer shell. Okay? This number here is smaller, right? Consequently, this value is greater. So we do not need the magnitude anymore. Yeah. Because you can simplify it further. This value is going to be greater than this one because this guy is less than this guy, right? So you don't need the magnitude anymore. We can go ahead and here write it in this way. Simplify as much as you can, right? AB goes upstairs and B minus AB stays downstairs. Here you go, like that. Capacitance. So it's 12:49 right now. One more minute to go. I think we can stop here right now. And there is just another thing that I want to cover about that. That's the dielectric I didn't cover. Yeah, let's do that next time on Wednesday. And then we close chapter 19 for the exam, okay? What is going to come is very straightforward. Here you go, capacitors and dielectrics. We cover capacitors, but the student didn't cover the dielectric portion, which we will do next time, okay? So I see you Wednesday. And if you need any help, I'll be having office hours right now.
Thank you.
Welcome.
Thank you.
Welcome.
Thank you, Professor. Have a good day.
You too.